In this video, I'd like to review the remainder theorem as well as synthetic division. Now, as a reminder, the synthetic division method is much quicker than using long division to divide two polynomials, and it's a useful way to check for divisors and factors of large polynomials. And we have this thing that's called the remainder theorem, and that's even quicker still than synthetic division for simple binomial divisions. This helps to identify the remainder when two polynomials are divided. Now, the remainder theorem does nothing to help us divide two polynomials, but it will help us to identify what the remainder is. A point to remember when using synthetic division is that the quotient, or the result of your division, compared to the original dividend, the number that you are dividing, the quotient is always 1 less. I should say the quotient's degree is always 1 less than the dividend. So in each of these cases, if I start with a b cubed, or n cubed in this case, the end result would end up being a b squared or an n squared. The degree is always 1 less than the original dividend. Now, in order to use synthetic division, we can only do that if we have what's known as a simple binomial, and that means that the coefficient of the variable is equal to 1. All of the examples that I'll show today in which we use synthetic division will meet this criteria. Finally, we place our coefficients of each term into the L chart, and we proceed. So if I were to use synthetic division to complete problem number 1 here, I would set up with 1, -1, -29, and +45 in my L chart, and then I would place a +5 on the outside, because again, we're not checking b minus 5 here as a factor. We're not dividing b minus 5 as a factor. We're utilizing the 0 from this factor, or the root from this factor, and that says that the root occurs at b equals +5. That's why we're using a +5 on the outside. So I bring the 1 down, this first number in our L chart, straight down, and I start multiplying 5 times 1. And I add these two together. -1 plus 5 is 4. Multiply these two. -29 plus 20 is 9. And 5 times 9 is 45. Oops, and I should be careful here. -29 plus 20 is -9. So 5 times -9 is -45, and this leaves us with a remainder of 0. So upon completion of this division, we have an end result, b squared plus 4b minus 9, with a remainder of 0. Now let's talk about that remainder theorem for just a moment. The remainder theorem will help us identify this 0 without going through the synthetic division. Now, the remainder theorem says that we can change the letter b in this case to the number 5, the number that we're investigating. And if we do that, the result of the calculation will give us our remainder. So let me set this up. 5 squared minus 29 times 5 plus 45. And the result of this calculation will be equal to the remainder of this polynomial division. Now, we'd like to think that this will equal 0, but let's check that out. Let's see what we get. And in order to do that, I might go to the TI calculator to complete this all in one step. So over on my calculator, I will enter the parentheses 5 to the third power minus 5 squared minus 29 times 5 plus 45. Now before I press enter, let me check to make sure that I have everything written correctly. 5 cubed minus 5 squared minus 29 times 5 plus 45. So that looks good. This looks just like our polynomial, but instead of b values, we've got the number 5 in place. And when I press enter here, my result should be equal to 0. And it is. So again, this is another way that we can check for a remainder without using synthetic division. Let's start with the remainder theorem here, and then we'll verify using synthetic division. So the remainder theorem might look like this. We're going to change the letter n in this case with the number -2. And remember, we're using -2 here because the factor of n plus 2 leaves us with a 0 at -2. So let's see what this does. -2 cubed plus 6 times -2 squared plus 6 times -2 minus 9. This result will be the remainder to our division problem. So let's see what we get. Okay, so I've entered the expression into the calculator, and I'm double checking it now. -2 cubed plus 6 times -2 squared plus 6 times -2 minus 9. Okay, that looks good. And when I press enter here, this will show me what my remainder is. And this is telling me that the remainder, after I do the division, should be -5. So let's check that out. Let's check to see if that's what we get. So I'll set up my synthetic division with a 1, 6, 6, -9, and a -2 on the outside. And now I will do the synthetic division silently. So hopefully you were able to follow along with that quickly here. And we did end up seeing that our remainder is -5. If I were to complete this division, my result would be n squared plus 4n minus 2 with a remainder of -5 over n plus 2. Let's try one more example here, number 5. I would like to complete the remainder theorem first, and then we will verify the remainder by using synthetic division. Okay, so I've entered this expression into the calculator. -6 to the 5th power plus 6 times -6 to the 4th power minus 9 times -6 minus 50. And when I press enter here, I get a result of 4. So that leads me to believe that the remainder is 4. Now be on the lookout for problems like this. When I set up the synthetic division, I will have to use a placeholder here, because I can use the 1 for the m to the 5th, the 6 for the coefficient of m to the 4th. Notice I don't have an m cubed or an m squared, so I'll use zeros in place of m cubed and m squared, and then -9m minus 50 with a -6 on the outside. And now I'll complete the synthetic division. And even with all of those zeros that popped in here, we were able to complete the synthetic division and saw that our remainder is 4, just as we predicted with the remainder theorem. So I hope this gives you one more tool to add to your toolbox when looking for factors of polynomials. We will complete one more set of notes for the career days, and we'll have that started in the next video.